at this very moment, while everything appears perfectly still, the ground beneath our feet is moving at over 1,000 miles per hour. The Earth is rotating on its axis, carrying everything on its surface in a continuous spin that has persisted for over 4 billion years. Simultaneously, our planet is orbiting the Sun at approximately 67,000 miles per hour, completing one full circuit every 365 days. The Sun itself, along with our entire solar system, is traveling through the Milky Way galaxy at around 500,000 miles per hour, taking roughly 230 million years to complete a single galactic orbit. And the Milky Way, home to hundreds of billions of stars, is hurtling through the universe at over 1 million miles per hour. Relative to the cosmic microwave background, the faint afterglow of the Big Bang itself. All of this motion is happening right now. Every atom, every molecule, every structure that makes up our world is participating in this complex dance of speeds and rotations. And yet, despite this tremendous cosmic velocity, we feel nothing. Absolute stillness. Complete calm. The sensation of motion is entirely absent. This paradox, the disconnect between the reality of cosmic motion and the experience of perfect stillness, stands as one of the most elegant puzzles in physics. Understanding why we feel still while the universe spins requires a journey through some of the most fundamental principles ever discovered about the nature of motion, space, time, and perception. The story begins with a principle so foundational to physics that it often goes unexamined. Yet it contains within it the key to understanding our experience of stillness. This principle concerns the nature of uniform motion. Motion that proceeds at a constant speed, in a constant direction, without acceleration or change. The remarkable insight, first clearly articulated by Galileo Galilei in the 17th century, is that uniform motion is physically indistinguishable from rest. There is no experiment that can be performed, no measurement that can be made, no observation that can reveal whether a system is moving uniformly or standing still. The two states are equivalent in every physical sense. This equivalence is not merely a limitation of our instruments or our senses. It is a fundamental property of the universe, built into the very structure of physical law. Galileo illustrated this principle with a thought experiment involving a ship sailing smoothly across a calm sea. He imagined passengers confined below deck, unable to see the water or the shore, and asked what experiments they could perform to determine whether the ship was moving or anchored in place. If they dropped a ball, it would fall straight down, just as it would on land. If they threw a ball to each other, it would travel through the air in the same arcs and trajectories. If they poured water, observed the flight of insects, or performed any mechanical experiment whatsoever, the results would be identical whether the ship was moving steadily forward or floating motionless. The interior of the ship would constitute a self-contained physical world, obeying exactly the same laws as the world outside, revealing nothing about the ship's state of motion. This insight, simple as it sounds, represents a profound shift in understanding. It means that motion is not an absolute property that can be detected in isolation. Motion is always relative, always defined in relation to something else. The implications of this principle extend far beyond ships and passengers. The Earth itself is like Galileo's ship, moving through space on its various rotations and orbits, carrying everything on its surface along for the journey. The atmosphere moves with the planet. The oceans move with the planet. Every mountain, every tree, every building, every grain of sand moves with the planet. And because all of these things share the same motion, because they are all passengers on the same cosmic vessel, there is no relative motion between them that could be detected. We do not feel the Earth's rotation because we are part of it, embedded within it, carried along by it so completely that there is nothing to feel. The air does not rush past because the air is moving with us. The ground does not shudder because the ground shares our velocity. Everything in our immediate environment participates in the same motion, and this shared motion is indistinguishable from rest. This principle was formalized and extended by Isaac Newton in his laws of motion, particularly the first law, often called the law of inertia. Newton stated that an object at rest will remain at rest, and an object in motion will remain in motion at constant velocity unless acted upon by an external force. This law captures the same insight that Galileo expressed, but frames it in terms of forces and accelerations. The natural state of matter is not rest, but uniform motion, and only forces can change that state. When no net force acts on an object, it continues in whatever state of motion it already possesses, whether that state is stillness or steady movement. The sensation of motion, the feeling of being pushed or pulled, arises only when forces act to change velocity, not from velocity itself. This distinction between velocity and acceleration is crucial for understanding the experience of stillness. Velocity, the rate of motion in a particular direction, cannot be felt directly. Acceleration, the rate of change of velocity, can be felt because it involves forces acting on the body. When a car accelerates from a stop, passengers feel pushed back into their seats because a force is acting to change their velocity. When a car brakes suddenly, passengers feel thrown forward because another force is changing their velocity in the opposite direction. When a car turns a corner, passengers feel pulled to the side because the direction of motion is changing, which is also a form of acceleration. But when a car cruises at a constant speed on a straight road, passengers feel no motion at all, only the vibrations and imperfections of the road surface, which are themselves small accelerations rather than the smooth motion of the vehicle. The Earth's rotation does involve acceleration, because rotation is a continuous change in direction, a constant curving of the motion that constitutes a form of acceleration, even when the speed remains constant. But this rotational acceleration is extraordinarily gentle. One rotation per day means the direction of motion changes by only 15 degrees per hour, a quarter of a degree per minute, an almost imperceptibly slow turning that produces very small accelerations. At the equator, where the rotational speed is greatest, the centripetal acceleration is about 0.0384 meters per second squared, roughly 1/300th of the acceleration due to gravity. This is far below the threshold of human perception. Our inner ears, the organs responsible for detecting acceleration and maintaining balance, simply cannot sense such tiny values. The accelerations we encounter in daily life, walking, turning our heads, standing up, are typically thousands of times larger than the acceleration from Earth's rotation. The orbit around the Sun involves even gentler acceleration because the orbital path has a much larger radius than the Earth itself. The centripetal acceleration keeping Earth in its orbit is about 0.006 meters per second squared, smaller still than the already imperceptible acceleration from rotation. and the motion of the solar system through the galaxy, the motion of the galaxy through the universe. These involve accelerations so minuscule, changes in velocity so gradual, that they are utterly beyond the reach of human sensation. We are bathed in motion, but blind to it, surrounded by velocity, but unable to perceive it, because perception responds to forces and accelerations, not to steady movement through space. This blindness to uniform motion is not a deficiency or a limitation in any negative sense. It is an elegant adaptation, a feature of perception that allows organisms to function effectively in their environment without being overwhelmed by irrelevant information. The evolutionary pressures that shaped human senses had nothing to do with cosmic motion. Early humans needed to detect predators and prey, to navigate terrain, to maintain balance while walking and running, to coordinate movements with precision and accuracy. None of these tasks required awareness of the Earth's rotation or orbital motion. An early human who could somehow feel the planet spinning would have gained no survival advantage, only confusion and disorientation. Natural selection, operating over millions of years, produced sensory systems tuned to the local, the immediate, the relevant, and indifferent to the grand motions of the cosmos. The result is a perceptual system beautifully matched to the physical principle of relativity. Because uniform motion is physically equivalent to rest, and because our senses evolved to ignore uniform motion, the experience of stillness accurately reflects our relationship to the immediate environment, even while obscuring our relationship to the larger universe. We feel still because we are still relative to everything around us, to the air, the ground, the objects within reach, the entire local frame of reference that defines our physical situation. This relative stillness is not an illusion. It is the truth of our local condition, even if it coexists with the larger truth of cosmic motion. Albert Einstein extended these ideas in his special theory of relativity, published in 1905. Einstein showed that the principle of relativity applies not only to mechanical experiments, but to all physical phenomena, including electromagnetism and the behavior of light. The speed of light is the same for all observers, in uniform motion, regardless of how fast they are moving, relative to each other, or relative to the source of the light. This constancy of the speed of light, combined with the principle of relativity, leads to remarkable conclusions about the nature of space and time. Measurements of length, duration, and simultaneity depend on the reference frame of the observer. Two events that appear simultaneous to one observer may occur at different times for another observer, moving relative to the first. Lengths contract, and time dilates for objects in motion relative to an observer. These effects, strange as they seem, have been confirmed by countless experiments and are essential for the operation of technologies ranging from particle accelerators to the global positioning system. For our purposes, the key implication of Einstein's relativity is the complete absence of any absolute standard of rest. There is no fixed background, no unmoving frame of reference, against which all motion can be measured. Every reference frame in uniform motion is equally valid, equally entitled to consider itself at rest, equally capable of describing the laws of physics correctly. When we say that the Earth is moving at 67,000 miles per hour around the Sun, we are describing the Earth's motion relative to the Sun. When we say the Sun is moving at 500,000 miles per hour through the galaxy, We are describing its motion relative to the galactic center. These are all relative statements, true within their respective frames of reference, but not absolute truths about the universe. In the reference frame of the Earth is at rest and the sun is moving. In the reference frame of the sun is at rest and the Earth is moving. Both descriptions are correct. Neither is more fundamental. This relativity of motion applies to the experience of stillness as well. When we feel still, we are experiencing our state relative to our local environment, and that experience is as valid as any other. There is no cosmic referee declaring that we are really moving and only seem to be still. The sense of stillness is accurate for our reference frame, and our reference frame is as legitimate as any other. This is not a philosophical position or a matter of interpretation. It is built into the mathematical structure of relativity, into the equations that describe how space and time work. Stillness is relative, motion is relative, and our experience reflects one perfectly valid perspective on a universe that can be described equally well from countless other perspectives. But this brings us to a deeper question. If motion is relative, if there is no absolute standard of rest, why does the universe seem to exhibit so much rotation? Everywhere we look, from the smallest scales to the largest, we find things spinning. Planets rotate on their axes. Moons orbit planets. Planets orbit stars. Stars orbit within galaxies. Galaxies rotate around their centers. Even clusters of galaxies show rotational motion. Rotation appears to be a universal phenomenon, present at every scale, built into the structure of the cosmos itself. If there is no preferred frame of reference, no absolute standard of motion, why should rotation be so ubiquitous? What makes spinning such a fundamental feature of the universe? The answer lies in a quantity that physicists call angular momentum, a measure of rotational motion that, like linear momentum, is conserved in isolated systems. Conservation of angular momentum is one of the fundamental principles of physics, rooted in deep symmetries of space and time. It means that the total angular momentum of an isolated system cannot change unless acted upon by external torques. A spinning figure skater who pulls in their arms spins faster because angular momentum is conserved. A collapsing cloud of gas spins up as it contracts because angular momentum is conserved. A planet forming from a disk of material acquires rotation because angular momentum is conserved. This conservation law ensures that any initial rotation, however slight, becomes amplified as systems collapse, condense, and organize themselves under gravity. The origin of cosmic rotation can be traced back to the earliest moments of structure formation in the universe. After the Big Bang, the universe was extraordinarily smooth and uniform, but not perfectly so. Tiny quantum fluctuations in the density of matter were stretched to cosmic scales during the period of rapid expansion known as inflation, creating slight variations in the distribution of mass. These variations acted as seeds for the growth of structure. Regions of slightly higher density attracted more matter through gravity, growing denser still, eventually collapsing to form the first structures, the protogalaxies and protoclusters that would evolve into the galaxies and galaxy clusters we observe today. As these structures collapsed under gravity, they didn't fall inward perfectly symmetrically. The distribution of matter around any collapsing region was never exactly uniform in all directions. There were always slight asymmetries, tiny imbalances that gave the infalling matter a net rotational tendency, As the collapse proceeded, and the material concentrated into smaller volumes, this initial rotation was amplified by the conservation of angular momentum, spinning the collapsing cloud faster and faster as it contracted. The result was rotation, emerging naturally and inevitably from the process of gravitational collapse, acting on even the slightest initial asymmetries. This mechanism explains why virtually every astronomical object rotates. The Sun rotates, completing one rotation roughly every 25 days at its equator. The planets rotate, each at its own rate, from the 10-hour days of Jupiter to the 243 Earth-day rotation of Venus. Moons rotate, asteroids rotate, even comets rotate as they tumble through the solar system. Stars throughout the galaxy rotate, some rapidly and some slowly, their rotation rates determined by their formation history and subsequent evolution. Pulsars, the rapidly spinning remnants of massive stars, rotate with extraordinary precision, completing multiple rotations per second, their regularity so reliable that they rival atomic clocks in accuracy. Galaxies rotate, with stars and their disks orbiting the galactic center in patterns that reveal the distribution of mass, including the mysterious dark matter that dominates the gravitational dynamics. At every scale, rotation is present, a universal consequence of gravitational collapse acting on imperfect initial conditions. But there is something curious about rotation that sets it apart from other forms of motion. Unlike uniform linear motion, rotation can be detected in an isolated system without reference to anything external. This was demonstrated by Newton with his famous rotating bucket experiment. If a bucket of water is set spinning, the water eventually spins with the bucket, and as it does, the surface of the water becomes concave, rising up the sides of the bucket due to the centrifugal effect. This concavity is a detectable consequence of the rotation, a physical effect that distinguishes the rotating bucket from a stationary one. No such effect distinguishes uniform linear motion from rest. A bucket moving in a straight line at constant speed is physically indistinguishable from a stationary bucket, but a bucket rotating is physically distinguishable from a stationary bucket. Rotation, unlike linear motion, appears to have a kind of absoluteness. This apparent absoluteness of rotation puzzled Newton and has occupied physicists ever since. If motion is relative, as the principle of relativity suggests, why should rotation be detectable while linear motion is not? Newton believed in the existence of absolute space, a fixed background against which rotation could be defined. He imagined that the water in the rotating bucket was spinning relative to this absolute space, and that the concavity of the water surface was a manifestation of this absolute rotation. But this interpretation has problems. If absolute space exists, it is undetectable, except through its effects on rotating objects, which seems unsatisfying as a physical explanation. And Einstein's theories suggest that there is no such absolute background, that space and time are relational rather than absolute. The resolution, still debated among physicists and philosophers, likely involves the distribution of matter in the universe as a whole. Ernst Mach, the physicist and philosopher who influenced Einstein's thinking, proposed that inertia itself might arise from the gravitational influence of distant matter. In this view, a rotating object is not rotating relative to absolute space, but relative to the average distribution of mass in the universe, the galaxies and clusters, and the cosmic background that fills the sky in all directions. The concavity of the water in Newton's bucket would then be a consequence of the bucket's rotation relative to this cosmic mass, not relative to some abstract absolute space. This idea, sometimes called Mach's principle, remains an active area of research and speculation in gravitational physics, and its full implications are not yet understood. For our purposes, the key point is that rotation involves acceleration, the continuous change in direction that occurs as an object traces a circular or curved path. And this acceleration is detectable even when linear velocity is not. The experience of stillness on a rotating planet is possible because the rotational accelerations are small, below the threshold of perception, but they are not zero. Sufficiently precise instruments can detect them, and sufficiently sensitive experiments can reveal them. The Foucault pendulum, discussed earlier, is one such experiment, demonstrating the Earth's rotation through the slow precession of the pendulum's swing plane. Ring laser gyroscopes can detect rotational motion with extraordinary precision, measuring the tiny differences in the paths of light beams traveling in opposite directions around a circular path. Satellites in orbit experience the effects of the Earth's rotation through the gravitational influences it creates. The rotation is there, real and measurable, even though we cannot feel it directly. The distinction between detectable rotation and undetectable linear motion reflects a deep asymmetry in the structure of physics. Linear motion respects the principle of relativity fully. Uniform linear motion cannot be detected in isolation, and all such motion is relative. Rotational motion partially respects the principle of relativity, in that the laws of physics are the same in all rotating reference frames, but it also involves real physical effects, centrifugal and Coriolis forces, that distinguish rotating frames from non-rotating ones. These effects are often called fictitious forces because they arise from the choice of a reference frame rather than from any physical interaction. But they are real in the sense that they have observable consequences for objects within the rotating frame. The Coriolis effect, for example, deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere, influencing the large-scale circulation of the atmosphere and the oceans, shaping weather patterns and ocean currents in ways that have profound effects on climate and life. This brings us to a remarkable feature of our experience. We live on a rotating planet, yet we do not feel the rotation, and we do not notice the Coriolis effect in our daily activities. The reason is scale. The Coriolis effect is proportional to the velocity of the moving object and to the duration of its motion. For small, slow, short-duration movements, like walking across a room or throwing a ball, the Coriolis effect is utterly negligible, far too small to detect or to matter. Only for large-scale, long-duration motions, like the flow of air across continents or the drift of ocean currents across basins, does the Coriolis effect become significant. We live our lives at scales where the Earth's rotation is invisible, where its effects are swallowed by larger forces and obscured by the noise of daily existence. The rotation is there, shaping the planet's atmosphere and oceans, influencing the weather we experience and the climate we inhabit. But it operates below the threshold of immediate perception, in the background of our awareness rather than the foreground. Let us turn now to the philosophical dimensions of motion and stillness, to the questions that arise when we contemplate our situation as beings embedded in a spinning cosmos. There is something almost paradoxical about our position. We are participants in tremendous motion, carried along at speeds that stagger the imagination, and yet we experience perfect calm. The universe is a whirlwind of activity at every scale, from the quantum fluctuations of empty space to the rotation of galaxy clusters spanning millions of light years, and yet we feel none of it. We sit in the eye of a cosmic storm that never breaks, passengers on a journey we cannot feel, travelers who never sense the motion of their vehicle. This experience of stillness in the midst of motion raises questions about the nature of reality and perception. Is stillness real, or is it an illusion created by our limited senses? Is motion the fundamental truth, and stillness merely a local approximation? The physics suggests that both stillness and motion are equally real, equally valid descriptions of the same underlying reality, depending on the reference frame from which they are observed. There is no hidden truth that says we are really moving and only seem to be still. The stillness is as real as the motion. Both coexist, both are accurate, and neither is more fundamental than the other. This coexistence of perspectives is one of the most profound features of relativistic physics. It suggests that reality is not a single, fixed thing that exists independently of observation, but rather a web of relationships, of perspectives, of ways of describing the same underlying phenomena. What is true from one perspective may differ from what is true from another, and both truths are valid within their respective contexts. This is not relativism in the philosophical sense, not a claim that truth is subjective or arbitrary. The laws of physics are the same in all reference frames, and the predictions they make are consistent and reliable, but the particular quantities that characterize a situation, the velocities and lengths and durations, depend on the frame from which they are measured, and different frames give different values, all equally correct. This multiplicity of perspectives extends to the experience of stillness. An astronaut in orbit around the Earth is in free fall, experiencing weightlessness, feeling no force and no acceleration even though they are circling the planet at thousands of miles per hour. From their perspective, they are at rest, floating in their spacecraft, motionless, relative to their immediate surroundings. From the perspective of someone on Earth, the astronaut is in rapid motion, traveling in a circular path, constantly accelerating toward the center of the Earth. Both perspectives are valid. The astronaut's experience of stillness is genuine as our experience of stillness on the Earth's surface. And yet, the two situations differ in profound ways. In the presence or absence of weight, in the curvature of space-time, in the paths through the gravitational field. Einstein's general theory of relativity, published in 1915, deepened this picture by revealing that gravity itself is a consequence of the curvature of space-time. Massive objects like the Earth curve the fabric of space and time around them, and this curvature guides the motion of other objects, causing them to follow curved paths that we interpret as gravitational attraction. An object in free fall, like the orbiting astronaut, is following a straight line through curved space-time, a path called a geodesic, the natural trajectory of motion in the absence of any force. From this perspective, gravity is not a force at all, but a geometric property of space-time, and the experience of weight is not the fundamental reality, but rather a consequence of being prevented from following the geodesic, of being held in place against the natural flow of space-time. This insight transforms our understanding of stillness and motion. When we stand on the surface of the Earth, we feel weight because the ground is pushing up against us, preventing us from falling toward the center of the planet, preventing us from following our natural geodesic through curved space-time. We are being accelerated constantly by the upward force of the ground, and this acceleration is what we perceive as weight. From this perspective, the astronaut in orbit is truly at rest in a deeper sense than we are, following the natural path through space-time without interference, while we, on the surface, are being pushed, accelerated, held in place by external forces. The experience of stillness on Earth is not the absence of acceleration, but rather a particular state of acceleration, matched to the gravitational field, balanced against the curvature of space-time, and therefore perceived as rest rather than as motion. This is a startling inversion of our intuitive understanding. We think of the astronaut as moving and ourselves as still, but general relativity suggests the opposite may be closer to the truth. The astronaut is following the natural flow of space-time, while we are being deflected from that flow by the solid ground beneath us. Our experience of stillness is not the absence of forces, but the presence of forces in a particular configuration. Forces that balance against gravity and create the sensation of weight that we interpret as normal, as restful, as still. The universe is curved, and what we call stillness is really a specific way of moving through that curvature, a way that feels natural to us because it matches the conditions under which human perception evolved. This brings us to another layer of the mystery. Why does the universe have the structure it does? The particular arrangement of matter and energy that gives rise to planets and stars and galaxies, to the gravitational fields we experience, to the curved space-time that shapes our lives. The answer lies in the history of the cosmos, in the processes that unfolded over billions of years to create the structures we observe, and ultimately, in the initial conditions, the state of the universe at its earliest moments, from which everything else followed. The current understanding of cosmology describes a universe that began approximately 13.8 billion years ago in an extremely hot, dense state, often called the Big Bang. In the earliest fractions of a second, the universe underwent a period of rapid expansion known as inflation, during which the fabric of space itself expanded faster than light, stretching quantum fluctuations to cosmic scales and setting the initial conditions for all subsequent structure formation. After inflation ended, the universe continued to expand and cool, passing through a series of phase transitions as the fundamental forces separated and the particles we observe today came into being. Matter clumped under gravity, forming the first stars and galaxies, which merged and evolved over billions of years into the cosmic web of structure we see today. Throughout this history, the conservation of angular momentum played a central role, ensuring that the slight initial rotations present in the early universe were preserved and amplified as structures collapsed and organized. The result is a cosmos filled with spinning objects at every scale, from planets to galaxies, all rotating as a natural consequence of the physical laws governing their formation. This rotation is not arbitrary or coincidental. It is inevitable, given the initial conditions and the laws of physics, a necessary outcome of the way matter collapses under gravity in a universe where angular momentum is conserved. But the initial conditions themselves remain mysterious. Why did the universe begin in the particular state it did, with the particular distribution of matter and energy, the particular values of the fundamental constants, the particular symmetries and asymmetries that gave rise to the structures we observe? These questions push beyond the boundaries of current physics, into the realm of speculation and conjecture. Some physicists suggest that our universe is one of many, part of a vast multiverse in which different regions have different properties, and we observe the properties we do because they are compatible with our existence. Others propose that the initial conditions might eventually be explained by a deeper theory, a theory of quantum gravity that describes the origin of the universe in terms of fundamental principles we have not yet discovered. These are open questions, active areas of research, frontiers of knowledge, where certainty gives way to exploration. What we do know is that the universe we observe is finely tuned for the existence of complex structures, for the formation of stars and planets, for the chemistry that gives rise to life, the expansion rate, the strength of gravity, the masses of the fundamental particles. All of these quantities have values that permit the existence of atoms, molecules, stars, planets, and ultimately, observers who can contemplate the cosmos and wonder at its structure. Small changes in these values would lead to universes very different from our own. Universes without stars or planets, without chemistry or life, without anyone to ask why things are the way they are. This fine-tuning is not necessarily evidence of design or purpose. It may simply reflect the selection effect of observation, the fact that we can only exist in a universe compatible with our existence. But it remains one of the deep mysteries of cosmology, a reminder that we do not fully understand why the universe has the structure it does, and within this structured universe, we find ourselves in a remarkable position. We are made of matter that was forged in the hearts of stars, assembled by gravity into planets, organized by chemistry into complex molecules. And somehow, through processes we are only beginning to understand, we have become conscious beings capable of contemplating our own existence in the nature of the cosmos. We are the universe becoming aware of itself, matter organized in such a way that it can ask questions about matter, energy, arranged in such a way that it can investigate energy. This is perhaps the deepest mystery of all, deeper than the mystery of motion and stillness, deeper than the mystery of cosmic rotation, deeper than the mystery of the initial conditions. How did the universe give rise to beings who can understand it? And what does it mean that we, tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, can grasp the principles that govern the cosmos on scales far beyond our direct experience? These questions do not have answers in the same way that questions about physics have answers. They are not the kind of questions that can be resolved by experiments or observations. They belong to philosophy, to contemplation, to the quiet reflection that accompanies deep curiosity about the nature of existence. But they arise naturally from the scientific investigation of motion and stillness, from the attempt to understand why we feel still while the universe spins. The answer involves physics, the principles of relativity and inertia, the conservation of angular momentum, the structure of space-time. But it also involves perception, evolution, the particular history of our species and our planet, and ultimately, the structure of the universe itself. the initial conditions from which everything else followed. The question is simple, but the answer spans the entire range of human knowledge. From the physics of motion, to the biology of perception, to the philosophy of existence. Let us return now to the concrete, to the specific features of our cosmic situation, and trace the connections between cosmic motion and human experience in more detail. The Earth rotates on its axis once every 23 hours, 56 minutes, and 4 seconds, a period known as a sidereal day, measured relative to the distant stars. This rotation gives us the cycle of day and night, the fundamental rhythm of human life since our earliest ancestors observed the sun rising and setting over ancient landscapes. The rotation axis is tilted relative to the plane of the Earth's orbit around the sun, inclined at about 23.5 degrees, and this tilt gives us the seasons, the variation in day length, and sunlight intensity that drives the annual cycles of weather, plant growth, animal behavior, and human activity. The rotation is remarkably stable, changing only very slowly over geological timescales. The tidal interaction with the moon gradually slows the Earth's rotation, lengthening the day by about 2.3 milliseconds per century. Earthquakes can cause tiny changes in the rotation rate by redistributing mass within the Earth. The seasonal movement of air and water masses shifts the rotation axis slightly, causing a wobble known as polar motion. But these effects are minuscule compared to the overall steadiness of the rotation, which has maintained its basic character for billions of years, providing a reliable foundation for the development of life and the evolution of complex organisms. The orbit around the Sun adds another layer of motion, carrying the Earth through space at an average distance of about 93 million miles from the solar center. This orbit is not perfectly circular, but slightly elliptical, bringing the Earth about 3 million miles closer to the Sun in January than in July. The variation in distance has only a minor effect on the seasons, which are dominated by the tilt of the rotation axis rather than the distance from the Sun. But the orbital motion is crucial for the existence of life, providing a stable energy source, regulating the temperature within the range that allows liquid water to exist, and maintaining the conditions that permit chemistry and biology to flourish. The Sun, in turn, orbits the center of the Milky Way galaxy, carrying the entire solar system along on a journey through the galactic disk. The Sun is located about 26,000 light-years from the galactic center in one of the spiral arms of the galaxy, surrounded by billions of other stars in various stages of their life cycles. The orbital period is approximately 230 million years, a span of time so vast that the Sun has completed only about 20 orbits since its formation 4.6 billion years ago. During each orbit, the solar system passes through different regions of the galaxy, encountering varying densities of gas and dust, passing through the spiral arms and the gaps between them, experiencing the changing gravitational environment of the galactic disk. The galaxy itself is part of a larger structure, the local group, a collection of more than 80 galaxies spread across a region about 10 million light-years in diameter. The Milky Way and the Andromeda Galaxy are the two largest members, gravitationally dominant, drawing smaller galaxies into their orbits and eventually consuming them through mergers. The local group is in turn part of the Virgo supercluster, a vast collection of galaxy groups and clusters spanning over 100 million light-years. And the Virgo supercluster is part of an even larger structure called Laniakea, a supercluster containing about 100,000 galaxies and spanning over 500 million light-years. At these scales, the motions become truly cosmic. Galaxies move relative to each other, under the influence of gravity, falling toward massive concentrations, streaming along filaments of the cosmic web, participating in the large-scale flow of matter through the universe. The Milky Way is currently falling toward the Virgo cluster, the dense heart of our supercluster, at a speed of several hundred kilometers per second. At the same time, the entire Laniakea supercluster is flowing toward a vast concentration of mass known as the Great Attractor, a gravitational anomaly located about 200 million light-years away, partially hidden behind the dusty plain of the Milky Way. And beyond all of this local motion, there is the expansion of the universe itself, the stretching of space that carries distant galaxies away from us at speeds proportional to their distance. This expansion was discovered by Edwin Hubble in the 1920s. Through observations of the redshift of distant galaxies, and it has since been confirmed by countless measurements and observations. The expansion is not motion through space in the ordinary sense. It is the expansion of space itself, the stretching of the fabric of the universe, and it means that the distance between any two galaxies that are not gravitationally bound increases over time. For distant galaxies, this expansion can exceed the speed of light, not because the galaxies are moving faster than light through space, but because space itself is expanding faster than light between us and them. This expansion creates a kind of absolute reference frame, not in the sense of Newton's absolute space, but in the sense of a preferred frame defined by the cosmic microwave background, the faint glow of radiation left over from the early universe. Observers, who are at rest relative to this background, see the radiation as nearly uniform in all directions. Observers, who are moving relative to the background, see a Doppler shift, with the radiation slightly bluer in the direction of motion and slightly redder in the opposite direction. Measurements of the cosmic microwave background have revealed that the solar system is moving at about 370 kilometers per second relative to this cosmic frame, toward a point in the sky in the direction of the constellation Leo. This is our peculiar velocity, the motion that distinguishes us from perfect co-movement with the expanding universe, and it reflects the gravitational influences of nearby structures pulling us in various directions. The experience of stillness that we enjoy is therefore not stillness relative to the universe as a whole. It is stillness relative to our immediate environment, to the planet and the atmosphere and the objects around us, all of which share our cosmic motion and therefore provide no indication of it. The motion is real, measured by instruments, confirmed by observations, essential for understanding our place in the cosmos. But it is motion that cannot be felt, motion that our senses are not equipped to detect, motion that operates in the background of experience while we go about our lives in apparent calm. This brings us to a final reflection on the nature of motion and stillness, on the relationship between physical reality and human experience. The universe is dynamic, constantly changing, filled with motion at every scale. Nothing is truly still. Even the most solid-seeming objects are composed of atoms in constant vibration, electrons in constant motion, quantum fields in constant fluctuation. Stillness in the absolute sense does not exist. What we experience as stillness is always relative, always a matter of perspective, always a comparison between ourselves and our surroundings. But this relative stillness is not less real for being relative. It is the foundation of our experience, the baseline against which we measure all motion, the calm center from which we observe the world. The fact that this stillness coexists with tremendous cosmic motion does not diminish it or expose it as an illusion. It reveals it as a different kind of truth, a truth about relationships and perspectives rather than about absolute states. We are still relative to everything that matters for our immediate experience, and that relative stillness is genuine, meaningful, and sufficient for all practical purposes. The physics of motion and stillness teaches us something about the nature of reality itself. It teaches us that reality is not a single fixed thing that exists independently of observation, but a web of relationships that can be described from multiple perspectives, each valid within its own context. It teaches us that the universe is far stranger than common sense suggests, that the principles governing motion at cosmic scales differ profoundly from the intuitions we develop through everyday experience. And it teaches us that we are deeply embedded in the universe we study, not external observers looking in from outside, but participants in the cosmic dance, made of the same stuff as the stars, subject to the same laws, part of the same ongoing process of change and evolution that characterizes the cosmos as a whole. The rotation of the Earth will continue for billions of years, gradually slowing under the influence of the Moon, eventually becoming tidally locked with one face permanently turned toward our nearest neighbor. The orbit around the Sun will continue as long as the Sun exists, carrying our planet through the changing seasons, through the slow evolution of the solar system, through the distant future when the Sun expands and our planet's fate becomes uncertain. The motion through the galaxy will continue. The motion through the universe will continue. The expansion of space will continue, and through all of this, the laws of physics will remain the same. The principles of relativity and inertia will hold, and stillness and motion will coexist, each as real as the other, each a valid description of the same underlying reality. There is something calming in this understanding, something reassuring about the order that underlies the apparent chaos of cosmic motion. The universe is not arbitrary or capricious. It follows laws that can be discovered, principles that can be understood, patterns that repeat across scales and contexts. The rotation of a galaxy follows the same principles as the rotation of a figure skater pulling in their arms. The orbit of a planet follows the same principles as the orbit of a satellite or the trajectory of a thrown ball. The experience of stillness on Earth follows the same principles as the experience of weightlessness in orbit, both consequences of the same fundamental physics applied in different circumstances. This unity of principles, this coherence across scales and contexts, is one of the great achievements of physics and one of the great wonders of the natural world. It suggests that the universe is comprehensible, that its structure can be grasped by minds like ours, that the same laws operate everywhere and at all times. We do not know why the universe has this character, why it is orderly rather than chaotic, why it follows mathematical principles that human beings can discover and understand. But we can observe that it does, and we can take some comfort in the order that reveals itself through careful investigation. The question we began with, why we feel still while the universe spins, has led us through a wide range of topics, from the physics of motion to the biology of perception, from the history of the cosmos to the philosophy of existence. The answer is multifaceted, involving principles of physics, features of evolution, structures of space-time, and patterns of thought. But at its core, the answer is simple. We feel still because motion is relative, because uniform motion is indistinguishable from rest, because our senses evolved to detect the relevant and ignore the irrelevant, and because the motions that carry us through the cosmos are smooth and steady, below the threshold of perception, hidden in the background of experience. This hiddenness is not a limitation to be overcome, but a feature to be appreciated. It allows us to live our lives without being overwhelmed by cosmic scales, to focus on the immediate and the practical, to experience calm even in the midst of tremendous motion. The universe accommodates us in this way, providing a stable platform for life and consciousness, a pocket of perceived stillness within the spinning cosmos. We are sheltered by the very laws that govern the motion, protected by the principles of relativity, cradled in the curved space-time of our gravitational environment. And when we become aware of the motion, when we learn about the rotation and the orbit and the journey through the galaxy, this awareness does not disturb our calm. It deepens it. It reveals a larger harmony, a grander pattern, a more beautiful structure than we could have imagined from our immediate experience alone. The motion is not threatening. It is the context in which we exist, the background of our being, the cosmic situation that makes our existence possible. Understanding the motion, tracing its causes, appreciating its scale, connects us to the universe in a way that ignorance could not, reveals our place in a structure far larger than ourselves, and invites contemplation of questions that have occupied human minds for millennia. The universe spins, and we feel still. And both of these facts are true, and their coexistence is not a contradiction, but a harmony, a reflection of the deep structure of physical law, a manifestation of the relativity of motion that Einstein revealed and that Galileo first glimpsed. We are participants in a cosmic ballet, moving without feeling the motion, spinning without sensing the spin, traveling without perceiving the journey. And in this strange, beautiful, paradoxical situation, we find ourselves at peace, calm within the whirlwind, still within the spinning, at rest within the motion that carries us through the infinite reaches of space and time. The stars continue their slow circuits around the galactic center. The galaxies continue their drift through the expanding universe. The cosmic web continues its evolution, structures forming and dissolving on timescales far beyond human comprehension. And through it all, on this small planet, in this corner of the cosmos, beings made of star stuff contemplate the nature of motion and stillness, asking questions that the universe itself cannot answer, finding meaning in the inquiry even when the answers remain incomplete. This is the human condition, perhaps the cosmic condition, to wonder, to question, to seek understanding of a universe that exceeds our grasp, but not our reach, that challenges our comprehension but rewards our curiosity, that spins eternally while we, embedded within it, feel the profound and wonderful calm of apparent stillness. The night sky holds its ancient patterns, the stars fixed in their constellations as our ancestors saw them, though we now know they are not fixed at all but moving in complex paths through the galaxy. Their apparent stillness, another manifestation of the same principle that makes the ground seem stable beneath our feet. Time passes imperceptibly as the earth turns and the seasons change and the years accumulate. And through all these changes, the fundamental laws remain the same. The principles of motion and stillness hold true, and the universe continues its endless dance, beautiful in its complexity, reassuring in its order, mysterious in its depths. We have traced the thread of this paradox through many domains of knowledge, from physics to philosophy, from cosmology to biology, and we have found that the answer is both simple and profound. Simple because it rests on clear principles: the relativity of motion, the conservation of momentum, the limitations of perception. Profound because these principles reveal a universe far stranger and more wonderful than everyday experience suggests. A universe where stillness and motion coexist, where perspectives multiply, where the same reality can be described in countless equivalent ways. The rotation continues. The orbit continues. The journey through space continues. And we continue with it, part of the motion, unable to separate ourselves from it, unable to stand outside and observe from some fixed vantage point. We are embedded observers, participants in the phenomena we study, making our measurements from within the system rather than from outside it. This embeddedness shapes our experience, determines what we can and cannot perceive, creates the illusion of stillness that is also, from another perspective, the reality of rest. There is no final word on this subject, no complete explanation that ties up all loose ends and answers all questions. The principles of physics explain why we do not feel the motion, but they do not explain why the universe has the structure that generates the motion, why the laws of physics take the form they do, why there is a universe at all rather than nothing. These deeper questions remain open, invitations to further inquiry, reminders that understanding is always incomplete, that every answer leads to new questions, that the process of learning never reaches a final destination. But this incompleteness is not a failure. It is the nature of knowledge, the character of inquiry, the condition of beings who seek to understand an infinite universe from finite perspectives. We learn what we can, we understand what we are able, and we remain curious about what remains beyond our current grasp. The question of motion and stillness has led us deep into the structure of physical law, deep into the nature of perception, deep into the philosophy of existence. It has revealed connections we might not have suspected, patterns we might not have seen, harmonies we might not have heard without asking the question. And so, we arrive at a place not of conclusion, but of continuing wonder. A place where the facts are clearer, but the mysteries remain, where understanding has grown, but questions persist. The universe spins. We feel still. These two truths coexist, each illuminating the other, each revealing something about the nature of reality that neither could reveal alone. The paradox is resolved, not by dismissing one truth in favor of the other, but by recognizing that both are aspects of a larger whole, a reality that contains both motion and stillness, both spinning and rest, both the cosmic dance and the calm at its center. This is where physics meets philosophy, where observation meets contemplation, where the human quest for understanding encounters the vastness of existence. The question is answered as fully as it can be answered at this time, with current knowledge, from current perspectives. But the exploration continues, for us and for all who will come after, as long as there are minds to wonder, and questions to ask, and a universe to investigate. The spinning goes on. The stillness persists, and somewhere in the relationship between them, in the harmony that makes motion feel like rest, and rest reveal itself as motion, lies a truth about the cosmos and our place within it that rewards every effort to understand and exceeds every effort to fully grasp. The hours have passed in this exploration, following the thread of a single question through the labyrinth of physics and philosophy. The journey has been long, but the destination is not an endpoint, only a resting place before further journeys. The universe offers infinite questions for those who seek them, and each question leads to others, and the process of inquiry has no end. What we have found tonight is one answer among many, one perspective among countless perspectives, one voice in the cosmic conversation that has been ongoing since the first minds began to wonder about the nature of things. And through it all, the earth continues to turn, carrying us through the darkness toward another dawn, spinning as it has spun for billions of years, moving through space as it has moved since the solar system formed from a collapsing cloud of gas and dust. The motion is constant. The stillness is constant. Both persist, both continue. Both remain true as the universe unfolds according to its laws, indifferent to our observation, but available for our understanding, vast beyond imagination, but accessible through patient inquiry. The question with which we began has opened doors to many rooms, each containing its own wonders, its own challenges, its own invitations to further exploration. Why do we feel still while the universe spins? The question is simple. The answer spans physics and biology, history and philosophy, the structure of space-time, and the nature of consciousness. It connects us to the cosmos on the deepest level, revealing that we are not separate from the motion, but part of it. Not observers of the spinning, but participants in it. Not distinct from the universe, but expressions of it. Matter become aware of itself, energy contemplating its own nature, the cosmos asking questions about its own structure. This is the strange loop at the heart of existence, the paradox deeper than the paradox of motion and stillness. We are the universe trying to understand itself, products of cosmic evolution, pondering cosmic evolution, the motion contemplating its own nature. There is no external vantage from which to view this process, no position outside the universe from which to observe. We are inside, embedded, part of the very thing we seek to understand. And yet, we make progress. We discover laws. We trace connections. We build understanding, piece by piece, question by question, from within the system we are studying. The rotation of the Earth is one small part of this vast structure, one manifestation of the principles that govern everything from subatomic particles to superclusters of galaxies. Understanding why we do not feel this rotation connects us to the whole, reveals the principles that apply everywhere, demonstrates the unity of physical law across all scales and contexts. The question is local, about our immediate experience. The answer is universal, about the nature of motion in space and time throughout the cosmos. And so the exploration ends where it began, with the experience of stillness that masks tremendous motion, with the calm that conceals cosmic velocity, with the peace that persists in the midst of the universal dance. The universe spins. We feel still. Both facts remain true, now understood more deeply. now connected to the vast web of physical law and evolutionary history that makes them possible. The paradox is not resolved in the sense of being eliminated. It is resolved in the sense of being understood, of being placed in context, of being revealed as not a contradiction but a harmony, not a puzzle but a pattern, not a mystery, but a manifestation of principles that govern everything that exists. The night continues, as nights always do, and the earth turns toward another day, as it always has, and somewhere in the darkness, minds rest while the cosmos dances, still in the midst of motion, calm in the midst of change, at peace in a universe that never stops moving, but always, from the right perspective, appears perfectly, beautifully, wonderfully still. There is more to explore in this vast subject, more connections to trace, more principles to examine. The nature of spin itself, that property that appears at every scale of existence, deserves closer attention. Spin is not merely rotation in the everyday sense. At the quantum level, particles possess an intrinsic property called spin that has no classical analog, that cannot be visualized as literal rotation around an axis, yet that behaves mathematically like angular momentum and has measurable consequences for the behavior of matter. Electrons have spin, protons have spin, neutrons have spin. Every particle in the standard model of particle physics carries this property, this intrinsic angular momentum that is as fundamental to its identity as its mass or charge. The spin of an electron is always the same magnitude, always 1/2 in units of the reduced Planck constant, never more and never less. This is one of the strange features of quantum mechanics, that certain properties come in discrete values rather than continuous ranges, that the microscopic world operates according to rules quite different from those that govern our everyday experience. The electron does not spin faster or slower. It has exactly the amount of spin it has, always, as a fundamental property of its nature, and this spin has consequences for everything, from the structure of atoms to the behavior of magnets to the operation of computer hard drives. The Pauli exclusion principle, one of the cornerstones of quantum mechanics, states that no two fermions can occupy the same quantum state simultaneously. Fermions are particles with half-integer spin, like electrons, and this principle explains why electrons in atoms arrange themselves in shells, why matter has the structure it does, why chemistry exists, why we exist. Without the exclusion principle, electrons would all collapse into the lowest energy state, atoms would be drastically different, chemistry as we know it would not exist, and neither would life. The spin of the electron, this abstract quantum property, underpins the entire structure of the material world. Bosons, particles with integer spin, behave differently. They can occupy the same quantum state, piling up in numbers limited only by the available energy. This property gives rise to phenomena like laser light, where huge numbers of photons occupy the same quantum state, moving in perfect phase, creating coherent beams of remarkable precision. It gives rise to Bose-Einstein condensates, exotic states of matter, where millions of atoms behave as a single quantum entity, displaying wave-like properties at macroscopic scales. The distinction between fermions and bosons, between half-integer and integer spin, shapes the entire structure of the physical world, from the stability of matter to the behavior of forces to the technologies that depend on quantum properties. This quantum spin connects to the classical rotation we have been discussing through the correspondence principle. The idea that quantum mechanics must reproduce classical physics in the appropriate limits, when scales are large and quantum effects average out. The angular momentum of a spinning basketball is quantized in the same units as the spin of an electron. But the quantum numbers involved are so enormous, so far from the small integers that characterize quantum systems, that the discreteness is utterly undetectable, swallowed by the continuous behavior of macroscopic objects. Classical rotation emerges from quantum spin in the limit of large systems, a continuous river emerging from countless discrete drops. The connection between quantum spin and cosmic rotation is not direct in any causal sense. The rotation of the Earth is not caused by the spin of electrons, and the spin of electrons is not influenced by the rotation of galaxies. These are phenomena at vastly different scales, governed by different aspects of physical law, connected only through the unity of the principles that underlie all of physics. But there is a conceptual connection, a recognition that angular momentum appears at every scale, that rotation is a fundamental feature of the physical world, that spinning is woven into the fabric of reality, from the quantum realm to the cosmic. The universality of rotation raises deep questions about the nature of space and time. Why should angular momentum be conserved? Why should rotation have this preferred status, detectable even in isolated systems, while linear motion remains relative and undetectable? The answer, as we have seen, involves the distribution of matter in the universe, the structure of space-time, the deep symmetries that underlie physical law. But these answers lead to further questions. Questions about why space-time has the structure it does, why the symmetries are what they are, why the universe exists at all with the properties it has. These questions may not have answers, at least not answers accessible to human investigation. They push against the limits of what science can address, the boundaries between physics and metaphysics, between what can be observed and tested and what must remain speculation. But the questions are worth asking, worth holding in mind as we contemplate the nature of motion and stillness, because they remind us that our understanding, however far it has come, remains incomplete, that the universe continues to hold mysteries that exceed our grasp. Let us turn to another aspect of the problem, the relationship between gravity and rotation, between the force that holds us to the Earth and the motion that could, under other circumstances, fling us away. Gravity is the dominant force at cosmic scales, the force that shapes the large-scale structure of the universe, that gathers matter into galaxies and clusters, that causes stars to collapse and black holes to form. It is also the force that creates weight, the sensation of being pulled downward, the feeling that tells us which way is down and which way is up. Without gravity, rotation would have very different effects. A rotating space station in orbit, far from any massive body, would create artificial gravity through the centrifugal effect, pushing occupants outward against the outer wall, creating a sense of weight that mimics gravity, but arises from rotation rather than from mass. This is the basis for many designs of space habitats, rotating cylinders or tori, that would provide their inhabitants with something like normal weight. Through the physics of circular motion, the occupants would feel pressed against the outer surface, would be able to walk and move normally, would experience up and down in a way that corresponds to their evolved expectations. But on Earth, rotation works against gravity rather than creating it. The centrifugal effect of the Earth's rotation pushes outward, opposing the inward pull of gravity, reducing our effective weight by a tiny amount. At the equator, where the rotational speed is greatest, this reduction is about 0.3%. At the poles, where there is no rotational motion around the axis, there is no centrifugal effect, and the effective weight is slightly higher. This variation is small enough to be imperceptible without precise instruments, but it has measurable consequences. The Earth itself bulges at the equator, its shape responding to the balance of gravitational and rotational forces, so that the equatorial radius is about 21 kilometers larger than the polar radius. This equatorial bulge is a visible manifestation of the Earth's rotation, a shape that could not exist for a non-rotating body. The Earth is not a perfect sphere, but an oblate spheroid, flattened at the poles and bulging at the equator, its shape determined by the interplay of gravity pulling inward and rotation pushing outward. Other planets show similar bulges, more or less pronounced depending on their rotation rate and their composition. Jupiter, rotating once every 10 hours, has a noticeable bulge visible even through small telescopes. Saturn, similarly rapid in its rotation, shows a similar flattening. These shapes are signatures of spin, visible evidence of rotation written in the geometry of worlds. The relationship between gravity and rotation becomes more complex in general relativity, where gravity is not a force in the ordinary sense but a curvature of spacetime. In this framework, rotating objects drag spacetime around with them, creating an effect called frame dragging, or the lens-Thirring effect. A satellite orbiting a rotating body like the Earth will experience tiny changes in its orbit due to this dragging, changes that have been measured by precision experiments like Gravity Probe B. The effect is extremely small for the Earth, but it becomes significant for rapidly rotating massive objects like spinning black holes, where frame dragging can have dramatic consequences for matter falling into the black hole. The interior of a rotating black hole, according to general relativity, is very different from the interior of a non-rotating one. While a non-rotating black hole contains a singularity, a point of infinite density at the center, a rotating black hole contains a ring singularity, a one-dimensional loop where space-time curvature becomes infinite. The region around this ring singularity has bizarre properties, including the theoretical possibility of closed time-like curves, paths through space-time that loop back to their own past. Whether these features reflect physical reality or merely artifacts of the mathematical idealization is unknown, since we cannot observe the interior of a black hole directly, but they illustrate how rotation affects the structure of space-time in extreme environments. At the other extreme of scale, the rotation of the universe as a whole has been a subject of investigation and speculation. Is the universe rotating? Does the cosmos as a whole have angular momentum? Observations suggest that if the universe is rotating, it is doing so extremely slowly, below the limits of current detection. The cosmic microwave background shows no clear signature of rotation, no systematic pattern that would indicate the universe is spinning. But the possibility cannot be entirely ruled out, and some theoretical models of cosmology incorporate global rotation as a feature of the universe's geometry. The question of universal rotation connects to the questions about absolute and relative motion that we discussed earlier. If the universe as a whole were rotating, what would it be rotating relative to? The very concept of rotation implies something to rotate relative to, some background or reference frame against which the rotation can be defined. For objects within the universe, that reference frame is provided by distant matter, by the galaxies and clusters that fill the cosmos. But for the universe as a whole, there is no external reference, no background against which to measure rotation. The question of whether the universe rotates may ultimately be meaningless, a question that assumes a framework that does not exist. These deep conceptual issues illustrate how the simple question of motion and stillness opens onto fundamental puzzles in physics and philosophy. The experience of stillness on a rotating planet is explained by well-understood principles, but those principles rest on foundations that are themselves mysterious, that lead to questions without clear answers, that connect our immediate experience to the deepest structure of reality. Let us consider another thread in this tapestry, the question of how rotation arises, how angular momentum enters the universe, where the spinning comes from. Conservation of angular momentum tells us that angular momentum cannot be created or destroyed, only transferred from one system to another. The total angular momentum of an isolated system remains constant. But this raises the question of where the original angular momentum came from, how the universe acquired the rotation that we observe at every scale. The answer, as we touched on earlier, involves the initial conditions of the universe and the process of structure formation. In the very early universe, before any structures had formed, the matter was distributed almost uniformly, with tiny variations in density caused by quantum fluctuations during inflation. These variations were random, statistical, with no preferred direction or orientation, but they were not perfectly symmetric. Any given region had slight asymmetries, slight differences in density from one side to the other, and these asymmetries translated into angular momentum when the regions began to collapse under gravity. Imagine a cloud of gas collapsing under its own gravity. If the cloud were perfectly spherical and perfectly uniform, it would collapse straight inward with no rotation. But real clouds are never perfect. There are always irregularities, always regions that are slightly denser on one side than the other. As the cloud collapses, these irregularities create torques, rotational forces that spin the collapsing material. The conservation of angular momentum then amplifies this rotation, spinning the cloud faster and faster as it contracts, until the rotation becomes a dominant feature of the resulting structure. This process explains why virtually every astronomical object rotates. The irregularities are inevitable, built into the initial conditions, a natural consequence of the quantum fluctuations that seeded all structure in the universe. No special mechanism is needed to create rotation. Rotation emerges naturally, inevitably, from the collapse of irregular distributions under gravity. The ubiquity of spin is not a mystery, but a consequence of fundamental physics applied to realistic initial conditions. But this explanation pushes the question back one step. Where did the quantum fluctuations come from? Why did the early universe have the particular pattern of fluctuations that it did? The answer involves quantum field theory and the physics of inflation, the period of rapid expansion in the first fraction of a second after the Big Bang. During inflation, quantum fluctuations in the fields driving the expansion were stretched to cosmic scales, imprinted on the fabric of space itself. frozen in as the seeds of all future structure. These fluctuations were random in a specific statistical sense, following the probability distributions predicted by quantum mechanics. But within those distributions, the specific pattern that emerged was one among many possibilities, a particular realization of a random process. This randomness is fundamental. There is no deeper explanation for why the particular pattern of fluctuations occurred rather than some other pattern. The laws of physics specify the statistical properties of the fluctuations, the probability distributions they follow, but they do not determine the specific outcome. The universe that emerged from inflation, with its particular arrangement of density variations, its particular distribution of matter and energy, is one possible universe among a vast ensemble of possibilities. And why this particular universe exists rather than another is a question without a clear answer. Some physicists interpret this situation in terms of a multiverse, a vast collection of universes realized from different random outcomes, each with its own pattern of fluctuations, its own distribution of matter, its own history and evolution. In this view, our universe is not special, not determined by any unique principle, but simply one among countless others, selected from the ensemble only by the fact that it contains observers to wonder about it. This interpretation is controversial, not universally accepted, and it may be untestable in principle, since other universes in the multiverse would be causally disconnected from our own. But it represents one way of thinking about the randomness at the heart of cosmic structure. Whether or not the multiverse interpretation is correct, the randomness in the initial conditions has profound implications for the nature of the universe we observe, the rotation of the Earth, the orbit of the Sun, the spiral structure of the galaxy. All of these features trace back to specific patterns in the primordial fluctuations, patterns that could have been different, that would have produced a different universe if they had been different. Our existence, our experience, our very ability to ask questions about the cosmos depends on a particular random outcome in the early universe, a roll of cosmic dice that could have come up differently. This contingency is humbling. The universe did not have to be the way it is. The laws of physics allow for many possible universes, and ours is just one realization of those possibilities. The experience of stillness that we enjoy, the beautiful balance of forces that makes our planet habitable, the entire structure of the cosmos that we observe. All of this rests on foundations that include irreducible randomness, outcomes that could not have been predicted, even in principle, events that simply happened to occur in the way they did. But contingency is not the same as meaninglessness. The universe that emerged from the random fluctuations follows orderly laws, exhibits predictable patterns, supports the emergence of complex structures, including life and consciousness. Within the randomness, there is order. Within the contingency, there is regularity. The laws of physics constrain what is possible, and within those constraints, the specific outcomes that occurred have led to a universe of remarkable structure and beauty. The rotation that appears at every scale is one expression of this order within contingency. The angular momentum that emerged from random initial conditions follows precise conservation laws, behaves according to well-understood principles, shapes the structures we observe in predictable ways. The randomness determined the initial distribution, but the evolution of that distribution follows deterministic physics, and the rotation we observe today is the necessary consequence of those initial conditions evolved according to those laws. Let us turn now to a different aspect of the problem. The question of how we know what we know. How scientists have come to understand the motions of the Earth and the cosmos. What evidence supports the picture we have been exploring? The history of this understanding stretches back thousands of years, from ancient speculations about the nature of the heavens to the modern precision measurements that confirm and refine our picture of cosmic motion. The idea that the Earth rotates was proposed by ancient Greek philosophers, including Aristarchus of Samos, who also proposed a heliocentric model of the solar system, with the Earth orbiting the Sun. These ideas were not widely accepted in antiquity. The dominant view, codified in the work of Aristotle and Ptolemy, held that the Earth was stationary at the center of the cosmos, with the Sun, Moon, planets, and stars revolving around it. This geocentric model persisted for over 1,000 years, supported by common-sense observation and by the philosophical and religious frameworks of the time. The revolution came in the 16th and 17th centuries, with the work of Copernicus, Kepler, Galileo, and Newton. Copernicus proposed a heliocentric model in which the Earth and other planets orbit the Sun, simplifying the mathematical description of planetary motions. Kepler discovered that planetary orbits are ellipses, not circles, and formulated the laws that describe how planets move. Galileo's observations through the telescope provided evidence for the Copernican model, including the phases of Venus and the moons of Jupiter. Newton unified terrestrial and celestial mechanics with his laws of motion and universal gravitation, explaining both the fall of apples and the orbits of planets with the same principles. The question of Earth's rotation was more difficult to settle directly. The rotation of the Earth explains the apparent rotation of the sky, the rising and setting of the sun, moon, and stars. But this apparent rotation could also be explained by an actual rotation of the celestial sphere around a stationary Earth. The two models make the same predictions for most observations. To distinguish them, one needed to find effects that depend specifically on the rotation of the Earth itself, effects that would not occur if the Earth were stationary and the sky were rotating. Several such effects were eventually discovered. The Coriolis effect, the deflection of moving objects due to the Earth's rotation, was predicted theoretically and confirmed through observations of large-scale atmospheric and oceanic circulation. The equatorial bulge of the Earth, the flattening at the poles, is a consequence of rotation and could not occur for a non-rotating body. The Foucault pendulum, demonstrating the rotation of the Earth through the precession of a pendulum swing plane, provided a direct and visible proof of the Earth's rotation that could be performed anywhere on the planet. The orbital motion of the Earth around the Sun was confirmed through the observation of stellar parallax, the apparent shift in the positions of nearby stars as the Earth moves from one side of its orbit to the other. This effect had been predicted by Copernicus, but was too small to detect with the instruments of his time. It was finally measured in 1838 by Friedrich Bessel, providing direct evidence that the Earth moves around the Sun. The small magnitude of the parallax, requiring precise instruments to detect, explained why ancient astronomers had been unable to observe it and had concluded that the Earth must be stationary. The motion of the Sun through the galaxy was discovered in the 20th century through observations of stellar motions and the distribution of stars in the Milky Way. The motion of the galaxy through the universe was revealed by measurements of the cosmic microwave background, which shows a slight Doppler shift indicating our velocity relative to the cosmic reference frame. Each layer of motion was discovered through increasingly sophisticated observations, each building on the previous, each adding to our understanding of our place in the cosmos. Today, our measurements of cosmic motion have reached extraordinary precision. The rotation of the Earth is measured to within fractions of a millisecond, with variations tracked continuously by networks of atomic clocks and radio telescopes. The orbit around the Sun is known with precision sufficient to navigate spacecraft to distant planets, to predict eclipses centuries in advance, to model the long-term evolution of Earth's climate. The motion through the galaxy and the motion of the galaxy through the universe are measured through multiple independent methods, cross-checked and refined to produce a consistent picture of cosmic motion on scales from the solar system to the observable universe. This precision is both a scientific achievement and a philosophical revelation. It shows that the universe is comprehensible, that its motions follow predictable laws, that measurement and analysis can reveal the deep structure of reality. The same principles that govern the fall of a stone govern the orbit of a planet, the rotation of a galaxy, the expansion of the cosmos. The universe is orderly, and its order can be discovered through patient observation and careful reasoning. But precision also reveals anomalies, discrepancies, places where observations do not quite match predictions. The orbit of Mercury precesses slightly faster than Newtonian gravity predicts, an anomaly that was explained by Einstein's general relativity. The rotation curves of galaxies do not match the distribution of visible matter, suggesting the presence of dark matter, an invisible component that interacts through gravity but not through light. The expansion of the universe is accelerating, driven by dark energy, a mysterious component that makes up roughly 70% of the cosmic energy budget, but whose nature remains unknown. These anomalies are not failures of the scientific method, but successes. Places where observation has outpaced theory, where the universe has revealed features that were not anticipated, where new understanding is waiting to be achieved. The study of motion, from Galileo's thought experiments to modern precision cosmology, illustrates the power and the limitations of scientific inquiry. We can measure, we can predict, we can understand to remarkable depth, but we also encounter mysteries, phenomena that resist explanation, features of the universe that exceed our current theoretical frameworks. The experience of stillness on a rotating planet is well understood, but the deeper questions, why the universe has the structure it does, why the laws of physics take the form they do, why anything exists at all, remain open, perhaps forever, beyond the reach of scientific investigation. Let us consider now the future of cosmic motion, the long-term evolution of the spinning universe, the fate that awaits the structures we have been discussing. The Earth's rotation is gradually slowing, losing energy to tidal interactions with the Moon. Roughly 4 billion years ago, the day was only about 15 hours long. Roughly 4 billion years from now, if current trends continue, the day will be significantly longer, perhaps 50 hours or more. Eventually, the Earth may become tidally locked to the Moon, as the Moon is already tidally locked to the Earth, with one face permanently turned toward its gravitational partner. The Moon itself is slowly receding from the Earth, moving outward at about 3.8 centimeters per year, stealing angular momentum from the Earth's rotation through the tidal interaction. This recession has been measured directly by bouncing laser beams off reflectors left on the lunar surface by Apollo astronauts, providing precise confirmation of the theoretical predictions. The recession will continue as long as tidal interactions persist, gradually weakening as the Earth's rotation slows and the tidal bulges become smaller. The Sun, too, is evolving. In roughly 5 billion years, the Sun will exhaust the hydrogen fuel in its core, expand into a red giant, and eventually shed its outer layers to become a white dwarf, a dense stellar remnant slowly cooling over trillions of years. The inner planets, including possibly the Earth, may be engulfed by the expanding Sun. The outer planets will continue to orbit the remnant, their paths altered, but not destroyed by the Sun's mass loss. The solar system will persist in some form, but it will be very different from the system we know today. On longer timescales, the galaxy itself will evolve. The Milky Way is on a collision course with the Andromeda Galaxy, approaching at about 110 kilometers per second. In roughly 4 to 5 billion years, the two galaxies will begin to merge, their stars passing by each other like two swarms of bees interpenetrating, their dark matter halos overlapping, their gas clouds colliding and igniting bursts of star formation. The merger will take billions of years to complete, eventually producing a single larger galaxy, sometimes called Milkomeda or Milkdromeda, with a structure quite different from either progenitor. Despite the drama of galactic collision, the stars within the galaxies will be largely unaffected. The distances between stars are so vast, relative to their sizes, that direct collisions will be extremely rare. The Sun, if it still exists as a white dwarf, will pass through the merger without encountering another star. The gravitational interactions will scramble stellar orbits, change the overall structure of the galaxy, but individual stars will persist, continuing their journeys through the newly formed galaxy. On even longer timescales, the universe itself will evolve. The expansion driven by dark energy will continue, carrying galaxies apart, stretching the distances between cosmic structures. Galaxy groups that are gravitationally bound will remain together, but unbound structures will be carried beyond the cosmic horizon, disappearing from view as their light becomes increasingly redshifted. The observable universe will shrink in a sense, as more and more of the cosmos becomes inaccessible to observation. Trillions of years from now, the stars will begin to die out. Star formation will cease as galaxies exhaust their gas supplies. The remaining stars will burn through their fuel, one by one, ending their lives as white dwarfs, neutron stars, or black holes. The universe will become dark, populated only by stellar remnants and the cold remains of planetary systems, drifting through an ever-expanding void. On still longer timescales, even these remnants will decay. Protons, if they are unstable as some theories suggest, will eventually decay, dismantling atoms themselves. Black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass extremely slowly, eventually disappearing entirely. The ultimate fate of the universe, according to current understanding, is a state of maximum entropy, a cold, dark, empty void where nothing more can happen, where all energy has been dispersed, where time itself becomes meaningless. This far future is almost impossibly distant, trillions upon trillions of years away. far beyond any timescale relevant to human existence. But it is the logical consequence of current physics, the extrapolation of known laws into the distant future. The spinning universe will eventually spin down. The motion will eventually cease. The structures we observe will eventually dissolve. Stillness, in this ultimate sense, awaits at the end of cosmic time. But this ultimate stillness is very different from the stillness we experience now. The stillness we feel is a local phenomenon, a relative condition, a balance of motions that creates the appearance of rest. The ultimate stillness of the far future is absolute, a true absence of motion, a state where nothing moves because nothing remains to move. Between our relative stillness and this absolute stillness stretches an almost infinite span of time, during which the universe will continue to evolve, to change, to exhibit the dance of motion and structure that characterizes its present state. The contemplation of cosmic timescales provides perspective on our current situation. The motions we have been discussing, the rotation of the Earth, the orbit around the Sun, the journey through the galaxy, are temporary in the cosmic scheme, features of a universe that is itself evolving, structures that will persist for billions of years, but not forever. Our experience of stillness is a snapshot, a moment in the long history of a changing cosmos. And even the planet we stand on, even the star we orbit, even the galaxy we inhabit, will eventually be transformed beyond recognition. Yet this impermanence does not diminish the significance of the present. The fact that the universe will eventually grow cold and dark does not make the present moment less real, less meaningful, less worthy of attention. We exist now, in this era when stars shine and planets orbit, and life flourishes. And this existence is as real as any other, as significant as any other, as worthy of contemplation as any other. The impermanence is itself a feature of reality, a reminder that nothing lasts forever, that change is fundamental, that the universe is a process rather than a thing. The experience of stillness, understood in this context, takes on new dimensions. It is not merely a subjective sensation, not merely a limitation of perception, but a window onto deep truths about the nature of motion, space, time, and existence. The stillness we feel connects us to the principles of relativity, to the structure of space-time, to the evolution of the cosmos. It is a point of contact between immediate experience and fundamental physics, between the personal and the universal, between the human scale and the cosmic scale. There is something remarkable about this connection. We are small creatures on a small planet, our lives measured in decades, our direct experience confined to a tiny fraction of the universe. And yet, we can understand principles that govern the entire cosmos, can trace the evolution of the universe from its earliest moments to its distant future, can grasp the nature of motion and stillness across scales from the quantum to the cosmic. This capacity for understanding is itself a cosmic phenomenon, a feature of a universe that has, through billions of years of evolution, produced beings capable of comprehending their own existence. The question we began with, why we feel still while the universe spins, has led us through a vast territory of physics and philosophy, history and speculation. The answer involves principles discovered over centuries of investigation, from Galileo's insight about uniform motion to Einstein's revolution in our understanding of space and time. It involves the evolution of our senses, the physics of rotation, the structure of the cosmos, and it connects our immediate experience to the deepest questions about the nature of reality. The stillness we feel is real as the motion that underlies it. Both are aspects of a universe that is stranger and more wonderful than common sense suggests. A universe where motion and rest are relative, where space and time are woven together, where the principles governing the smallest particles are connected to the principles governing the largest structures. We are embedded in this universe, made of its substance, subject to its laws, and through our understanding, we become aware of our own cosmic situation, aware of the spinning that feels like stillness, aware of the motion that underlies the calm. This awareness is itself a kind of stillness, a mental quiet that accompanies deep understanding. When the confusion of contradictory intuitions is resolved, when the paradox of motion and stillness is explained, there's a settling, a calm, a peace that comes from comprehension. The universe no longer seems arbitrary or chaotic, but ordered and comprehensible. The experience of stillness is no longer puzzling, but explained, connected to fundamental principles, placed in the context of cosmic evolution. And so we arrive at a resting point, not a final answer, but a place of understanding, a point from which the vast landscape of physics and philosophy can be surveyed. The universe spins, from quantum particles to galactic superclusters. We feel still because of the relativity of motion, the smoothness of cosmic velocities, the limitations of our evolved senses. Both facts are true, both are aspects of reality, both are connected through the deep structure of physical law. The night sky, if we could see it, would show the slow wheeling of the stars, the apparent rotation of the heavens that is really the rotation of the earth beneath us. The moon would trace its path across the sky, reflecting sunlight from its position in orbit around our planet. The planets would wander among the stars, following their own orbits around the sun, tracing paths that have been calculated and predicted with extraordinary precision. And beyond what any eye could see, the galaxies would be receding, space itself expanding, the cosmic story unfolding according to laws discovered through centuries of investigation. All of this motion surrounds us, carries us, includes us, and yet we feel still. This is the paradox we set out to explore, and this is the resolution we have found. The stillness is real because motion is relative. The motion is real because the universe is dynamic. Both truths coexist. Both are accurate descriptions of the same underlying reality. And our experience reflects one valid perspective on a cosmos that can be described equally well from countless other perspectives. The exploration has been long, the territory vast, the questions deep. But the central insight is simple. Motion and stillness are not opposites but complements, not contradictions, but aspects of a unified reality. The universe spins and we feel still, and both of these facts express the same deep truth about the nature of space, time, and existence. The spinning creates the conditions for stillness. The stillness arises from the spinning. And we, embedded in this cosmic dance, experience the profound calm that comes from being perfectly synchronized with the motion around us. There is nothing more to add, no further resolution to achieve. The paradox is explained. The mystery is illuminated. The question is answered as fully as it can be answered with current understanding. What remains is simply the experience itself, the stillness that persists, even as we now understand the motion it contains, the calm that deepens with comprehension rather than being disturbed by it. The universe spins on, as it has for billions of years, as it will for billions more, and we, spinning with it, feel the peace of perfect alignment, the stillness that arises from motion, the rest that emerges from the cosmic dance. The cosmos continues its ancient patterns. Stars fuse hydrogen into helium in their cores, releasing the energy that makes them shine. Planets trace their elliptical paths around those stars, held in gravitational embrace. Moons orbit planets. Asteroids tumble through the void. Comets trace their elongated paths through the inner solar system. Galaxies rotate, their spiral arms sweeping through space. Their stars orbiting the galactic center in journeys that take hundreds of millions of years to complete. And through all of this motion, on every world where observers might exist, the experience of stillness persists, the calm that arises from shared motion, the peace that comes from being part of the cosmic flow. This is the final understanding, the deepest truth that emerges from our exploration. Stillness is not the absence of motion, but the harmony of motion, not the opposite of spinning, but its natural consequence when all things spin together. We are not separate from the cosmic dance, but part of it. Not observers of the motion, but participants in it. And our experience of stillness reflects our perfect integration into the spinning universe. The paradox resolves into unity. The contradiction dissolves into harmony. The question leads to an answer that is also a deeper question, an understanding that is also a mystery, a resolution that is also an opening to further contemplation. And so the exploration ends where it began, with the experience of stillness in a spinning universe, now understood more deeply, now connected to the vast web of physical law and cosmic evolution. The universe spins. We feel still. Both are true, and in that truth lies a beauty and a mystery that no explanation can exhaust, that invites continued contemplation, that rewards every effort to understand, while always pointing toward deeper questions, further mysteries, more profound truths waiting to be discovered. The rotation of the Earth continues, marking time as it has since the planet formed from the solar nebula 4.5 billion years ago. The orbit around the Sun continues, carrying our world through the seasons, through the years, through the slow evolution of the solar system. The journey through the galaxy continues, the Sun moving along its path around the galactic center, passing through the spiral arms, traversing the spaces between them, participating in the grand rotation that characterizes our cosmic home. And the galaxy itself moves through the universe, part of larger structures, influenced by larger forces, connected to the cosmic web that spans the observable universe. All of this motion, from the quantum spin of electrons to the rotation of superclusters, exhibits the same fundamental principles, the same conservation laws, the same underlying physics. Angular momentum is conserved. Rotation emerges from collapse. Motion is relative. Stillness is perspective. These simple principles, discovered through centuries of investigation, explain the paradox we set out to explore, connect our immediate experience to the structure of the cosmos, reveal the deep unity that underlies the apparent diversity of natural phenomena. The scientific investigation of motion continues, pushing into new territories, revealing new phenomena, raising new questions. Gravitational wave detectors now sense the ripples in space-time caused by merging black holes and neutron stars, opening a new window on the dynamics of the cosmos. Space telescopes observe the universe at wavelengths invisible to human eyes, revealing features that were previously hidden. Particle accelerators probe the quantum world with ever greater precision, testing the foundations of our understanding. Each new observation, each new discovery, adds to our knowledge, refines our understanding, connects our experience to the vast structure of physical reality. But even as our knowledge grows, the fundamental experience remains the same. We feel still. The ground beneath us seems solid and stable. The air around us seems calm and motionless. The sensation of rapid movement through space is entirely absent, replaced by the quiet that characterizes normal experience. This experience is not changed by knowledge, not altered by understanding. The stillness persists whether we are aware of the motion or not, whether we understand the physics or not, whether we contemplate the cosmos or simply go about our daily lives. This stability of experience in the face of expanding knowledge is itself remarkable. Learning about the Earth's rotation does not make us feel the rotation. Understanding the orbit around the Sun does not create a sensation of orbital motion. Knowledge changes our intellectual picture of reality, but not our immediate perceptual experience. The stillness is robust, stable, unchanged by what we learn about its cosmic context. This robustness reflects the deep structure of perception, the way our senses process information, the evolutionary history that shaped our nervous systems. We perceive what is relevant to survival and action, not what is true about the cosmos at large. The cosmic motion is irrelevant to finding food, avoiding predators, navigating terrain, coordinating with other people. Evolution did not equip us to perceive it, and no amount of intellectual knowledge can create perceptions that our brains are not built to generate. But intellectual knowledge can change how we interpret our experience, how we understand our situation, how we relate to the cosmos. Knowing about the motion that underlies our stillness does not make us feel the motion, but it does connect us to a larger story, a deeper reality, a more comprehensive picture of existence. The stillness becomes richer when it is understood as relative, as arising from harmony, as connected to the spinning universe. The experience is the same, but its meaning is transformed. This transformation of meaning through understanding is one of the great gifts of science. The world appears the same whether we understand it or not, but understanding adds depth, connection, significance. The night sky is beautiful whether we know what the stars are or not, but knowing that they are distant suns, many with their own planets, some with conditions potentially suitable for life, adds dimension to the beauty, connects our experience to a larger story, places us in context. The same is true for the experience of stillness. The stillness is pleasant whether we understand its cosmic context or not, but understanding that context, knowing about the motion that underlies the calm, adds depth to the experience, reveals connections that were previously hidden, transforms a simple sensation into a window onto the structure of reality. And so the exploration concludes, not with a definitive ending, but with a transition back to experience, back to the stillness that has been our subject, back to the calm that persists through all our investigations. The understanding we have gained is now part of how we experience stillness, part of the context in which the sensation occurs, part of the meaning that accompanies the perception. The universe spins on, indifferent to our understanding, continuing its ancient motions regardless of whether anyone observes or comprehends. Stars rotate, planets orbit, galaxies turn, and the cosmic dance continues as it has for billions of years. Within this dance, on this particular planet, at this particular time, we experience the stillness that arises from harmony, the calm that emerges from shared motion, the peace that comes from being perfectly synchronized with the spinning cosmos. This is the strange and beautiful truth that our exploration has revealed. Motion and stillness are not opposites but aspects of the same reality. The spinning creates the stillness. The stillness reflects the spinning. And we, caught in the middle, experience the profound peace of perfect alignment with a universe in constant, ceaseless, eternal motion.